You get an A. I mean, if you earn it. If you earn it. I give people A's every day if they earn it. Okay. One more time, real fast. What is the maximum number of pieces you could break an electron into? A common answer here is 6.25 times 10 to the 18. Let me reflect on this for a second. Suppose eggs were like atoms or whatever, okay? There's still 12 eggs in a dozen. If I ask you how many pieces can you cut an egg into, does it make sense that since there are a dozen eggs in a carton, that you can cut an egg into a dozen pieces? Is that logically followed? 6.25 times 10 to the 18 is not the number of pieces of the electron. 6.25 times 10 to the 18 is the number of electrons in one coulomb. If you got 6.25 times 10 to the 18 electrons, that's like a dozen eggs. It doesn't mean you can cut an electron into a dozen or anything. The correct answer for A is 1. Nobody has ever split an electron. You may have noticed this in your chemistry class. You can have an atom with a +1 charge or +2 ionization, but you ever in chem, has everyone taken Gen Chem? No. Who has not taken Gen Chem? Ever. Everyone has taken Gen Chem. Has anyone in any of your chemistry classes ever had an ionization of, helium plus 1.2? Plus 1.5? No, it's helium plus 1, plus 2. Electrons aren't splittable. As it turns out, protons and neutrons are. It's just the scale of energy it takes to break apart a proton or a neutron is way bigger than anything chemical reactions break apart. You gotta have a fancy pants physics lab or a certain astrophysical phenomena in outer space to break apart protons and neutrons big time. Like neutron stars, black hole mergers, supernovas, that kind of thing. The correct answer is 1. More of you got this than 3 o'clock. I'm still on the knife edge. Let me ask you this. I'm going to present you a little bit of information and see if the logic follows along. There is a particle called a proton. Duh. There's a particle called the electron. The proton is positive, the electron is negative. So far, hopefully, this is all reviewed. There is also something that exists in the real world that actually is real. It's not sci-fi, called antimatter. Antimatter protons are called, you'll never believe this, antiprotons. There are such things called antineutrons. But the name for anti-electrons is way sexier. They're called positrons. Positrons have positive charge. In every other way, but electric charge, but charge, positrons behave exactly like electrons. You can put a positron and an antiproton together and measure its properties, and it's exactly like ordinary hydrogen. Except which side is plus, which side is minus gets switched, which inside outside is plus and minus. Yeah.
You said positron is what?
Positron is positive. Antiproton is negative. Yeah. Well, it's not an electron, it's a positron, but it has exactly the same properties in every other way, but it's quantum numbers as an electron. Moreover, here's actually an important thing to know about the nature of electric charge. Not even in the most sophisticated experiment or astrophysical observation that's ever been made have we ever made different numbers of electrons appear in the world, or different numbers of the positrons exist come into being, except if we make them in pairs. You can make matter. Your chemistry instructors lied to you when they said that matter is conserved. Mass is not conserved. Also, I lied to you last semester when I said to you energy is conserved. That is a lie. Energy is not conserved. Mass energy is conserved. The total amount of kilograms plus the total amount of joules with a conversion factor is conserved. You can turn pure energy into mass. You can create particles that did not exist before. I have done it personally. Not with my own two bare hands. It takes a whole physics lab to do it. You can also destroy from existence particles. Whenever I have destroyed an electron in real life, and I have done this, whenever I have destroyed an electron in real life, it takes a positron. Whenever I have created an electron in real life, I also create a positron. Hey, if I create a plus and a minus at the same time, have I changed the total charge of the universe? If I destroy a plus by adding a minus, have I changed the total charge of the universe? No. No physics process ever at all, even a little bit, has ever been observed that changes the total charge of the universe. That's a principle you can rely on that goes deep. Total mass energy conservation, by the way, is probably almost certainly true as well. Okay, but that's relativity, you don't need that. Okay, so facts about protons, positrons, electrons. You should also know that protons, neutrons, and electrons are what we harp on in like your entire education, because that's what you're made of, man. Like in the entire Earth, I don't know how many, but maybe, 10 positrons exist. I'm only slightly lying to you. I'm not sure, to be precise, but like those 10, probably 9 of those 10 are in physics labs. They're hard to make. Whenever they bump into electrons, they vanish in a flash of energy. And they turn into light. The electron and the proton, no, positron together vanish off and turn into pure energy. Yeah.
Thank you.
What? Well, if you take a piece of light and accelerate, or actually any charge, if you take anything at all and give it a redonkulous amount of energy, then pass it near the electric field of the atom or whatever, you can spontaneously turn its motion energy into mass energy. You can congeal its kinetic energy into mass form. And when we do this, the amount of mass that we create and the amount of energy that is lost are connected via a formula that you have heard before. Do you know the formula? E equals mc squared. Have you heard of that? That's the relationship between energy, form, and mass form. Equals mc squared. That's what that means. Okay, but that is relativity, and we don't need that. Not for this class, anyway. I've told you a fair few things about protons, electrons, and positrons now. I challenge you to tell me how many protons, electrons, and positrons there are in a singly ionized helium atom. I will remind you that helium is atomic number uno, dos, sorry, forgot about hydrogen existing. Okay, so I'll tell you, I've got singly ionized helium, helium plus 1. You've all taken chemistry class. Yeah. How many protons are there in helium? It's atomic element number 2. How many electrons and how many positrons are there? How many protons are there in the nucleus of the helium? How many electrons are there in the electron shell? How many positrons are there in the positron shell? Okay, when I say a letter before the question, that means you answered in there. Please don't put all 3 things in B, my dudes. I'm sorry, yes, question? Yeah. I love you all, but please listen to the format. What is a positron? I just told you what a positron is. Come in late. Positron is an antimatter version of an electron. It has positive charge, and every other way it behaves exactly like an electron, except it's positive. When it smashes into an electron, when it gets close, they collide and vanish in a flash of pure energy. And you should also know that they don't exist and mass in the world. It's possible to make them one at a time in a particle physics laboratory, but they're not a normal part of the world around you. Yeah, you guys don't know the symbols here either. P plus, what's P plus? What's E minus? E plus? Positron. Also, I said it out loud. How many protons, electrons, and positrons make up a singly ionized helium? Oh my God, that makes me so much happier. People weren't knowing the symbols. That's why you were answering. Okay. Okay. Life is better. Life is not great. Still a lot of wrong answers, but better than I was afraid. Helium is atomic number 2. That means there are those protons, 2 protons in its nucleus. That's what makes helium helium. Helium is defined by having 2 protons in its nucleus. Correct answer for B is 2. If it's atomic number 2, then 2 protons. As I said before, I'm going to skip to D. As I said before, positrons aren't a constituent of the real world around you. Not, well, I shouldn't say real world, the everyday world around you. There are no positrons around you. If you're calling somebody in fear of the positrons and they ask, is the positron in the room with you right now? The answer is no, not unless you're going to my lab. So there are no E pluses in a normal helium plus 1 atom. So if we've got +1 total charge and 2 protons, how many electrons must there be? You have 1 minus, cancel out one of the minuses in the 2 plus. Yeah? Yeah? Correct answers were 2, 1, 0. Okay. Oh my God, and the 1 plus was hidden. I still had a bunch of people tell me that helium plus 1, the helium ion has 2 electrons. Hey, if you just didn't see the fact that it's ionized or listened to me 3 times when I said it, was it because that was covered up? What? Come back. Okay. I'm gonna move on. I feel like reading comprehension or listening comprehension was okay here. And no, seriously, in the 3 o'clock section, there were so many wrong answers, but it may be because of things like this. I wrote the symbol and I didn't explicitly say this means positron, that means proton. And people might guess that P and P both mean positron. I don't know why they thought this meant proton, but harsh question.
I was asking, like, what is the significance of positron? Like, why do we make it as an important?
I've got a Lego set that I love. It's a castle. It's got a bunch of gray blocks and black blocks. And if the castle people, the Lego people were alive, they might think that there are 2 colors in the world, black and gray. But the real world has many colors in it. And if you want to understand the nature of light and color and pigments and all that and plastics, you have to understand the full spectrum of colors. Ants might or might not know that there's a third, not ants go down definitely, well, bugs, cockroaches may or may not know that there is a 3rd dimensional space. They're constrained to live on the floor, right? They live on basically a 2-dimensional surface. They're not birds, thank God. Cockroaches don't know about up and down. They might not think about up and down in their teensy weensy gross little brains.
Thank you.
Oh, that's terrifying. I'm going to proceed to forget that fact and to preserve my sanity. Well, my point is, you got something that stays on the surface of the earth. Its tiny little brain might not understand or think about the fact that up, down is an important same as left, right, and out. For the entire course of human history, people can walk around, but the scale of jumping up and down into outer space perhaps was never considered. The fact that there might be outer space took thousands of years, at least in Europe, to catch on. 100 years in Europe to catch on because people had this mental model. The Ptolemaic universe was that there is no place outside the sky. The sky must be a solid dome with the stars painted on it, right? You know about the Ptolemaic model? Oh, way back when, people thought that the stars were painted on a big glass sphere. They didn't think there was anything outside the glass sphere. They thought God was outside the glass sphere. But they didn't perceive that they didn't have the idea of the ability to go up being unlimited.
Actually, there were many like stupid theories in
Sure. Sure, but we learn better. And here's a piece that now I'm learning you better about the nature of matter. There's more to matter than protons, neutrons, and electrons. You can break protons and neutrons down. There are things called positrons. There are things called muons, neutrinos, quarks, stuff that you never heard of before. It's all part of the fabric. And if you want to understand all the rules of the universe from a deep level, profoundly, and truly the complete universe, you got to know all the pieces. That's why physics. That's why physicists. That's why my field. Yeah, right. Philosophy done. Okay, so I am reasonably content. Let's do some numbers. I'm going to give you my number. No, we'll skip this. No, wait, one more concept. Which is stronger? I'm not talking about direction, just the strength. 1 nanocoulomb worth of protons or 1 nanocoulomb worth of electrons? What is this? Google form E. You got an equal number of protons, an equal number of electrons. If I've got 6 billion protons, 6 billion electrons, which makes a bigger electrical oomph, which is stronger electrically? Protons, neutrons, or are they equal? Am I lying to you? Tricking you. Which has a stronger electrical effect? If I ignore direction, are protons stronger or electrons stronger?
You just put whichever we think.
Yeah, which exerts bigger electrical forces on objects nearby? Screw 1 nanocoulomb. Screw 1 nanocoulomb. I've got 1 electron. I've got 1 proton. Which pulls the other harder? Here's Google form. What do we have? E? This E?
Yeah.
Okay. Google form E. I got 1 proton and 1 electron. Which pulls the other harder? Which exerts the stronger electrical influence? Google form E. No, it's not E, it's F. What you talking about, foo? You're trying to trick me. Google form F. If I just hold up a single proton near a single electron, which pulls harder? Which pulls exerts the greater force on the other? One more time. I hold up an electron. I hold up a proton. I asked which experiences the bigger, did I say experiences or causes? Which causes the bigger force, right? On the other. Not energy, force. Tell me about the force. Which exerts a greater force on the other? Protons pull harder or do electrons pull harder intrinsically? Push or pull? I'm going to do this with experimental mathematics. Let's say I've got 2 coulombs worth of electrons and 3 coulombs worth of protons. Hell, I'll give the protons an advantage. Let's see if it makes a difference. Okay. 2 coulombs worth of electron charge. Maybe I should say -2. Screw it. 3 coulombs worth of proton charge. The force formula QE, test charge times electric field, yeah? the electric field formula, KQ, source charge over distance squared? Right? Deja vu? Okay, so let's plug in some numbers. Which is bigger? Or which of these expressions is bigger? You may reconsider your answer to F, whether protons or electrons pull harder in light of this. I'm hoping to guide you Socratically to see. Which experiences the bigger force in these? This would be if the electrons are test charge. In this case, this force would be protons are test charge. And R is the same. I mean, the distance from one to the other is the distance from the other to the one. You can't have one be further from the other than the other is to the one. Let me ask this again in Google Form G. Hold on. Google Form G. Which of these two expressions is bigger? Google Form G. Nope. Just is the first expression bigger? Is the second expression bigger? Are they the same? Are both expressions equal to 0? Or hey, I ordered a cheeseburger. Exactly. 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 So if electrons being the test charge and protons being the test charge cause the same force, then which is intrinsically stronger? Neither. Electrons move more because they're lighter. We care in electricity about talking about electrons so very much because the same force is exerted on a proton and an electron, and the electron is less massive, so it goes flying. Look, do you guys know how much more massive a proton is? Roughly? 2,000. Call it 1,000. Call it 1,000. Okay. So I've got a kilogram of electrons and 1,000 kilograms of protons. Okay. I let them sit near each other and I put them at a distance so they get, I don't know, 1 Newton of force. I hold them at whatever distance it takes to get 1 Newton of force. I want you to tell me which accelerates more. They both feel 1 Newton of force. You now know that the force 3 times 2 is 2 times 3, man. The force that each exerts is the same. So Newton's third law guarantees that has to be. So the force is the same. The protons are 1,000 times more massive. Which accelerates faster? Put it in Google form. Google form H. Let me be specific. Force on both is 1 Newton. The mass of the electrons is a kilogram. The mass of the protons is 1,000 kilograms. I'm rounding the hell out of these things. I challenge you to tell me, what is the ratio of the accelerations? Find acceleration of protons to electrons. There we go. Electrons accelerate more, less, the same. What is that ratio? God willing, you remember how force and mass are related to acceleration. If not, go back to 111, you punks. Fma. Okay, so we can solve this explicitly. If I use the equation Fma
1 equals 1 times, what's the acceleration of the electrons? 1. A electrons equals 1. If I use the formula, F equals ma, what's 1,000 times what equals 1? Right? Am I lying? The protons accelerate more or less. Which number is bigger, the proton acceleration or the electron acceleration? Google form, look at the numbers on the screen. The protons accelerate with an acceleration of 0.001. The electrons accelerate with an acceleration of 1 meter per second squared. Which of these two numbers is bigger? Google form I. I? I? I. I. Again, acceleration of the protons, we have just discovered, versus acceleration of the electrons. Methinks the acceleration of the electrons is a rather larger number. 1 is rather bigger than 1/1000th. Yeah? I challenge you. Look, here's an additional homework problem. I give you additional homework problem. Yeah, ready for your additional homework problem? Very important. Worth 100% of your grade. I want you to all go out and kick a football player, then go kick a newborn. Equal strength. What's going to happen other than you getting beaten up and arrested and me getting arrested? The newborn's going to go flying. Which accelerates more? The newborn, right? You apply equal force to a little thing, he goes spew. You apply equal force to a big thing, it goes, you just made a big mistake. I mean, you made a big mistake in either example. Right? Right? Okay, so the electrons, do they feel the bigger or smaller force? What did we just say about the force that the electrons exert versus the force that the protons exert? Which of these is a bigger number? 2 times 3 or 3 times 2? They're the same. So which experiences the bigger force? They're the same. 3 times 2 equals 2 times 3. Force is force is force is force is force. Electrons and protons cause the same electrical force. Does that mean they experience the same acceleration? No. Which accelerates more? I've got a couple of people talking. Hold on, Harsh, 2 seconds. I want to see it. I want to see it. Google form J. Which accelerates more? You now know. No, I'm not going to say it a fourth time. All right, question.
Actually, that question would be wrong if I.
Okay.
It was like F is equals to P.
True.
I was thinking, so if the charge of the proton and the electron is same,
Yes.
then
Nice.
would there be an equality in the sort of
Nope. No. Yes. Absolutely. At the same distance, a proton and an electron cause the same magnitude.
So the charge of the particle is positive, right?
Yeah.
So
Precise.
yeah, so charges of the which is Q, so one.
Yeah. Oh, so where's the little q is test?
That's fine.
Okay. Then
So
Theo.
if Q is same and since they are same, they'll have full electric field,
Yes.
then
Force is equal. Exactly. My whole point. Well, half of my point. Exactly. Okay. So again, we done said that we have equal forces because 2 times 3 equals 3 times 2. We said F equals ma means little things accelerate more when you have equal forces. The correct answer is that electrons accelerate more. If that does not make sense, please rewatch the video here. This is important. I am going to put a question to this effect on the test. I will ask you something like 3 microcoulombs of charge or 1 centimeter away from negative 2 microcoulombs of charge. The 3 microcoulombs of charge are made up of protons. I don't know, which experiences a greater force? Which will experience the greater force? Exactly equal. And if I tell you the masses, which would experience the greater acceleration? The lighter one, exactly. Good. Okay. Now let's plug in numbers. I want you guys to find the electric field around the Bohr radius of a hydrogen atom of hydrogen. Okay, so I'm going to give you hydrogen. Merry Christmas. Have a hydrogen. What is this? K. Find E. Magnitude of a electric field of a proton. Electric field due to a proton at radius. Oh God, what is the Bohr radius? Half an angstrom. So that's 5 times 10 to the minus 11 meters. I will remind you. Actually, I'm going to give you a whole bunch of constants, and you have to think about what is important. The K constant, 9 times 10 to the 9. The mass of an electron, what the hell, is 9.11, 10 to the negative 31. Mass of a proton is 1836 times the mass of an electron, I think. What else could you possibly need to know? What else could you possibly not need to know? Yeah, I'll give you that. Oh, right, the charge. Charge of an electron. Mm, mm, mm. Electric field's a vector. I didn't make a big deal about this before. Electric field has a direction. You can push towards or away. It can be facing towards or away. I'm asking just for magnitude here, okay? Don't tell me a negative number. If I want you to tell me the magnitude, that is a plus or a minus number, I will explicitly tell me the magnitude and direction. Harsh.
Please, like, small q, a, capital Q by R square, right?
KQ on R squared, K source Q on R squared, and the force formula equals test charge times electric field. There, that's everything you could possibly need to know.
What was small q, a, capital Q divided by R?
Well, Q times E would give you the force all in one. But I'm not asking for force in this part. Yeah, I will. R is not the correct answer. I'm asking for a number of newtons per coulomb. Hey, I should actually start getting picky about that. I'm gonna start getting picky and smack you guys down if you don't. Give me with units. How to specify a number, a united quantity. If the answer is x is 5 meters, what I want you to say is 5 space m. Okay, the units for electric field are newtons per coulomb. So your answer should be some number space n divided by c. Okay, yeah. N newtons per coulomb. Newtons, not newtons. Here's a hint. Hint two. Coulombs are lots of electrons. If you had 1 Newton per Coulomb, that's a really small number of newtons per individual. Really huge number of newtons for an individual. If you've got an individual, no, never mind. Plug in the numbers. You should be able to plug in the numbers. Check yourself. The correct answer is on the board. Gesundheit. Hey, please with your calculator, please make sure that you can type numbers in and get an answer. If you cannot, you're screwed in this. You have to be able to plug in numbers. Take a minute, make sure that you can get this. The biggest thing that I see people screwing up is not putting parentheses around downstairs. If you've got a fraction, the downstairs needs parentheses. No. Capital Q is the source charge. By asking for the field of a proton, the proton is causing the field, is the source charge. So the strength of the proton is what's important here. How strong is a proton compared to an electron? Exactly equal strength, opposite sign. I tell you the charge on an electron, doesn't matter that this is whatever I'm going at. Yeah, you see? Charge.
The calculation when I made the calculation there. So twice.
I'm sorry? Wait, hold on. Wait. You did 8 divided by B to C, then 8 divided by C. That second part should be C. Phew, I thought you broke arithmetic for a second. Or were you trying to trick me? Okay. I didn't ask an L yet. Okay, so challenge dose. Next question. Do question L. Real fast as you can. Calculate like a speed of light. How many newtons would a coulomb of charge sitting there feel? Chop. You have 5 seconds to do it and enter it. I put 1 coulomb of charge. Can you figure out at light speed the force on a coulomb of charge sitting there? I put a coulomb of charge, utterly impossible, at this position, and I ask you what is the force?
Time's up. Put in the answer. You're right. Okay, now turn to your neighbor and talk about it for a second. I've got the electric field. I'm telling you that I put 1 coulomb of charge to feel that field. Turn to each other and talk about the meaning of the electric field, and you could change your answer if you like for L. 2 people got it right. Again, you're asked to find the force when 1 coulomb of charge is placed in a field of 5.8 10 to the 11 newtons per coulomb.
You see it? Yeah. I'm seeking to know. Don't find that. I'm so confused about it. Did I relate to that?
What?
Coulomb is the standard unit, so we calculate everything in lumens.
But no, it's right, it's a number of particles in the effect, so you're asking.
Hey, I said this in passing, but I didn't make a big deal about it. The coulomb is the unit of charge. If I write Q equals 1, and I want to calculate numbers with Q, I use 1. Q is 1 if I say 1 coulomb, not 6.25 10 to the 18. There are 6.25 times 10 to the 18 individual particles in 1 coulomb, but we use coulombs in all of our calculations. Whenever you see Q, you should be plugging in coulombs. Does that change your answers? Okay. Think about that. 1 second left. Good. Not good enough, but good. Okay, here's the correct answer. If electric field is equal to 6 and force is equal to charge times electric field, then force equals 1 times 6 is 6. Well, let's see. 6, it's actually 6 times 10 to the 11. It's the same number. That's what electric field means. Electric field tells you how many newtons 1 coulomb experiences. That's the whole point of it. 2 before an M. How much force do 2 coulombs feel? I put 2 coulombs magically at 1 volt radius from a proton. How many newtons do 2 coulombs feel? I will remind you that the electric field is roughly, I'm not telling you directions, 6 10 to the 11. And now I say, what is the force? You type in LaTeX, nerd. Person who put /C dot. I love you, but you're a nerd. Okay, let's do this. Force equals charge times field. What's charge? 2. What's field? 6. 2 times 6? 12 times 10 to the 11, not 10 to the 30. 10 to the 30 is astronomical force. Like, I don't know, the sun on the earth probably exerts 10 to the 30 newtons. I don't know. Now, the force of that many newtons would also rip holes in space-time if you put a coulomb. That's because a coulomb, 2 coulombs is a redonkulous amount of charge. Let's do one more try. Let's do one more try. See if we can get to better here. What is the force on an electron? This is what is actually realistic. There is an electron orbiting at the Bohr radius around a hydrogen proton. The force a proton exerts at the electron. What is the force that and I'm going to erase where I multiply 2 times 6 and where I multiply 1 times 6 so you can see the numbers before. Did you see where I got the 6, by the way? I just rounded 5.8 because I don't want to math. Just the magnitude for now. You express that as 1.1610 to the 12th, that's fine too. Multiply carefully, please. Just like in sex ed. N, find the force that the proton exerts on an electron. I've given you electric field. You can find the charge. It's right there. And I can't write straight. Not even my writing is straight. A. Gina, I would love it if you would ask. It would make me extraordinarily happy. Get inside your skulls. If you used coulombs, it'd be the same thing. You have to use coulombs. That's what I just said. Coulombs are the SI unit of charge. You must use coulombs. You must use coulombs. That's why I tell you these numbers in coulombs. Gina, let me ask a follow-up question. What quantity is coulombs measuring, and what quantity is force? Damn it, I said it again. Is F measuring? If I ask you the force in newtons, what is a coulomb in relationship to that? You correctly stated F equals QE. Correct, Gina. Good. Coulomb does measure electric charge. Okay. So we are using coulombs in this equation. We are using coulombs when we plug into the electric charge of the electron. Q for an electron is 1.6 10 to the negative 19 coulombs. 1.6 10 to the negative 19 standard units. One fundamental charge. Oh, makes sense. Good. Getting better, but we're still not there yet. Oh, I'm going to give the happier numbers. I have a field magically made of 7 newtons per coulomb. I have a charge of 6 coulombs. What force does it feel? Yes, Gina, and it's something like 1 with 30 zeros after it times stronger. Gravity is absurdly weak compared to electricity between fundamental particles.
Out of 1.6 is the 10 and 6.85 megaparsec cells, 18 electrodes to have a charge of 1 coulomb. Then how can we put a polymer when we cannot break the one?
So we can break up a coulomb if the coulomb is one of things. You can split up a dozen, or you can put those apart into 12 piles. You can have one X.
No, I'm asking. So if there are 6.25 or 10 to the power electrons would have electric field then how shouldn't we could have said like 6 into 10 to the power electrons. How can we break the electron? Like how can we add 0.5?
Multiply those two numbers together, 6.25 becomes 1.6.
What's the scientific
Yeah, it's simple. 1.6, 6.25.
No, I was asking like, I was confused when we put a decision, it's 25, but I realized it's the scientific notation.
Oh, I'm rounding too.
And then-
I always round. It's 1.60 something and 6.25 something. It's not exactly that, but this is precise enough. Good, good, good. 42 newtons. Google question P. Real fast. Half as much charge. How much force? Real fast, fast as you can. If I cut the charge in half, how much force would that 3 coulombs feel? Fast as you can. Faster, faster, faster. Okay, so if I multiply 7 by 3, I get half as much as when I multiply 7 by 6. Correct answer is 21. So Q, what if I have twice as much charge? How much force would 12 coulombs feel in that field? Fast, 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 faster. Okay, so if I have Q times electric field
and Q is twice as great, and electric field does not change, I get twice as much as when I had 6. If 6 times 7 is 42, 12 times 7 is twice as much as 42. 84 newtons. Yeah. The whole point. Well, philosophical for half a second, please don't not pay attention. Is we could talk about electrical strength just by tabulating. If I hold up this much charge, this would be the force. If I hold up that much charge, that would be the force. If I hold up this much charge, that would be the force. You know, make tables of how much I did a whole butt ton of scientific experiments holding this charge, that charge, and the other charge up and measuring the force that some electrical phenomenon exerts. But the magical thing is the ratio is always the same. The ratio of the force exerted on some test charge divided by the amount of test charge there is always the same. Each proton in a source, in a test charge, each proton in each electron in a test charge feels the same amount of force. So if you double the amount of electrons, you double the amount of force. If you triple the amount of free electrons, you triple the amount of force. It scales linearly. If you divide force by number, you get back to force per one. And we don't use force per one electron, we use force per coulomb's worth of electrons. But still, the idea of electric field is just how much does one standard unit, how much force does one standard unit experience, and you can scale from there. There was one more thing I wanted to do. One more place I wanted to go with this. What would feel 1 Newton of force? R. How much charge would it take to feel 1 unit of force? 1 Newton. You can write as a fraction if you wish. I mean, it's unanswerable if you don't know. If I don't give you a field, you can't. Oh, thank God. Good. 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 Okay, if I set up the equation. 7 force, force equals charge times, god damn it, equals charge times field. And I say, I want to solve this for Q, 1/7. Yes, good. So far, everyone got it right. Okay, last thing, here's a homework problem. You want a homework problem done for you? Merry Christmas. Here's a homework problem. When we're done with this, we go. Giga Chad? What? I don't remember the exact details, but it's like something just exactly like this. I'm gonna put some positive charge there, negative charge. My convention, the convention I've always seen is red is positive, blue is negative. And the tick sizes are 1 centimeter. It's a 1 centimeter grid. That's actually almost to scale on my screen. And I'm gonna put -2 nanocoulombs there. No, forget nano. We've been doing that too much. Millionth of a coulomb there. And 5 microcoulombs there. I think the way the homework system said it, put it up, was it gave you XY coordinates. Draw the graph X comes horizontal, Y comes vertical. If you can't see it in your head, draw it. Draw the coordinate axes. So if I put this in text on a test, I would say something like a -2 microcoulomb charge at the origin and is at the origin, I can't words, and a 5 microcoulomb charge sits at xy equals 0. What is that? 3? I can't count. Oh my God. And your challenge is find, what are we on? ST? There is a trick here. You can plug in -q if you want, but you're probably going to screw it up. We're finding force and field. I screw it up if I'm not stupidly careful, super careful. The strong suggestion I have to make is plug in positive numbers for charge in the force formula and reason about, is this attracted or repelled? The plus and minus charges attract each other or repel each other? If the minus charge is pulling on the plus charge, which direction is that force, up or down? Plus or minus? Minus is exerting an upward force? Really? Yeah. What is the -2? Yeah. If I asked about the negative charge, it would be exactly flipped. Oh, sure. Sorry. Okay. K 9 billion. It's actually 8.99, but whatever, screw it. That's everything. You don't need, you should have the formula by now. Oh, what the balls. There. Watch the units. Watch the units or they might run away. S is magnitude, T is direction. Oh, you did put that, good. Watch the formula carefully. Arizona's canceled sex ed. That's why people are having trouble multiplying. 9 minus 6 is 3. 3 plus 4 is 7. 9 over 9 is right. Right. I'm saying. Yes. And I'm doing that in the same way that I want. Nope, I don't want you to do it that way. I want you to do this as the test charge. Yes, good. Ah, I had forgotten that this is a common goof. But it is. Thank you, person who asked why is R3. Because the meaning of R is the distance from source to test. The distance between those two is 3. I don't have a circle that I'm finding a radius of. Well, actually, I kind of do. If I make a circle around the source charge of 3 centimeters radius, the field at any point along that circle will be the same. That's why I use R. I can find a place of constant force magnitude, constant field magnitude, and then it is the radius of a circle. But I do not cut the distance between the two charges in half. That is R. What did I just say about minus? Don't use minus. Magnitudes are always plus. If you get 100, you can go. If you got 100, you get out of here. You're good. If you didn't, I'll walk you through it. Direction, real fast. Hey, direction on what? Muy importante. If you get it flipped on what, you will always get it wrong. If I asked you the force on the positive, you ask yourself, is this attracting or repelling? Opposites charges attract. So imagine being the positive and attracted downward. Downward is the correct answer for directions.
As negative y.
Negative y, sure, you could say it that way too. Okay, if you have not got a 100, if you want to get a 100 on the test, please look at this on the right-hand side. Here is the plugging in the numbers. You must be able to plug in numbers. If your calculator appears to be lying to you, please come up here and I will show you what the goof is. I promise.
So the direction is going downward because
Yes.
the electrons are going towards the.
No, because I'm asking about the force on the positive charge. Positive charge
Okay.
is attracted. Which direction is it attracted? It's attracted that way.
Downward, okay. Okay, that makes sense. Okay, thank you.
Good. Sure. Ciao, horse.
Oh my God, why did they do that?
Please.
So I understand, the formula. I just don't understand where the 2 times 10 to the 16 from.
Negative. What's a micro?
Okay,
Micro
gotcha, gotcha.
million. And it's negative, 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 negative. Micro million. That's it.
Okay, the 3 is the distance and then that also in micro. Okay.
No, I didn't say micrometers. What did I say?
Oh, centimeters. Okay.
C doesn't stand for micro. Yeah. Correct, yes, let me look at it now, otherwise let me hit stop. Sure. Wait, other questions?